Hi everybody, welcome to the first section in Calculus 3. In this section, we study vectors in plane. So vectors, we already know that in some sense. In the plane, by a plane here, we mean two-dimensional space. And now we define vectors. So perhaps you learned this in trigonometry, but certainly you have to know this in pre-calculus. So how do we define a vector? So a vector will have two things, the magnitude and the direction. What it doesn't have is location. So magnitude and direction, and there's no location. Meaning that if we have the vector, we will have the length or the magnitude and then the direction. And two vectors are equal if they have the same length and direction. Length or magnitude are the same. So the length here is the same as the magnitude. Right. So if we have a vector like that and we have the same vector, let's say about this. I suppose the lengths are the same and they point in the same direction, so those vectors are equal. Now, one thing very important is the notation for vectors. As you see the notation for vector, we use the boldface U and the boldface V. If we cannot write the boldface, then we will use this in the handwritten. It will be notation for vector. If we cannot type like that, if we have to write, we can say U as a vector or V as a vector, or we can write the vector in that sense, PQ with the head, with the arrow head in front of it. This is the boldface. Boldface U. Right. So we will distinguish a vector with a boldface and with the different numbers called the scalar. Scalar has no direction. So scalar has no direction. Right. So as you see, in the first definition we have here, given a scalar C, so you see we write the regular C for a scalar that has no direction, and the vector V, that is the boldface. The scalar C times V is the vector whose magnitude is C, absolute values of C multiplied by the magnitudes of V. Right, so that is absolute value. If C is positive, then CV has the same direction as V. If C is negative, CV and V point in opposite direction, and they are parallel if they are scalar multiple of each other. So when we say those two are parallel, the direction though doesn't matter. It can point that direction or opposite direction, as long as they point in whether same direction or opposite direction. We can call them parallel, as long as one is the multiple of the other. Right. So let's look at the first example. Write the vector, the following vector in terms of U and V. So first vector PQ. PQ point in the same direction as U, as vector U, and have the same length. So we say PQ is equal to vector U. I'm going to use boldface. And also somebody will use U with the arrow head in front of it, on the top of it, still fine. But in this book, and what I prefer to, we use the boldface to distinguish a scalar. Right, QP is pointed opposite direction. So we're going to say that's going to be negative U. And then next, QR. QR pointing the same direction as V, but it's going to be twice as long, right? So we're going to say that is going to be 2 times vector V. And then RS. Because it has the direction, so I clearly indicate what is the tail and what is the head of the vector. So RS is the same direction as U, but opposite direction and 3 times as long. So we say going to be negative 3 vector U. Right, RS 3 times vector U, but opposite direction. QR 2 times vector V, same direction. QP opposite direction. And PQ same direction as U. Right, that's simple enough. Right, so that is just a vector multiplied by a scalar. Now, what's next is we do the sum of the vectors and then the difference of the vectors. So first the sum. There are 2 ways to do that. One is called the Parallelogram Rule. The other one is the Triangle Rule. So first, our vector has no location, right? So when we can add them, we can move them as we want to. Let's say it's easier if we have a grid. Let's say we have vector U horizontal like that, vector U, and then vector V like that. Now, when we add them, we just move the vectors as we want to. Let's see, that will be okay, that much. So one way to do this is we do triangle rule. So first we have the vector, we move that vector here, it's no problem. Vector has no location, we can just move them freely. And how long is this one? Okay, an inch. Right. So we move the head, move the second vector so that the tail of the second vector is on the head of the first vector. So this triangle rule sometimes referred to head to tail. It's the head to tail, so the tail of the second head one is the head of the first one. And I have a professor, he was in an army, and he said he preferred that as heel to toe. Just like when you're walking, the heel of the front foot is on the toe of the back foot. So we just do that. And when we do that, the vector like this, from beginning to the end is the sum. So that is triangle method. The parallelogram, we're going to move so that both of the tail end will be the same. Then this is about 1 inch. So we're going to put the tail at the same point. Again, vector has no location, we can just move them freely. And then with this we can form a parallelogram. and then the diagonal. And this is the parallelogram rule. And this is the triangle rule. It's better to just draw that. And then for the difference, we just turn the vector backward and we still do the same thing. Right, that should be easy now. Let's look at an example. Write the following vector as sum of the scalar multiple v and w. So first, vector OP. Right, so we get to O to P. We go 1W, 2W, and then 2V, 3V, 1, 2, 3. So in that case, what we use is head to tail method or triangle rule. So OP is going to be 2W and then 3V. Right, OQ. Right, to get from O to Q, we're going to go 1V, 2V, 3V, and then going down. This is opposite to W. Oh, that's just a V. So OQ, 3V, and then minus the W. Notice the notation I use for the vector, the bone face, that is. Now, QR. So it doesn't matter how we get from Q to R. We can go from this direction first. So that is a V, and then a W, a W. So we have a V plus 2W. So that's nice and all. Physically, we can find the sum or the difference of vectors like that. However, it would be better if we can do this mathematically without drawing. Right, so how do we do this? So to do that, we define a vector in the what we call the standard position, or just the position vector. Now, once again, pay attention to the notation. So now, first of all, we have a vector bone face V with the tail at the origin meaning the point 0 for x, 0 for y, and the head, it says v1, v2. Notice that this is a point. That's called the opposition vector. And the notation for vector, to distinguish between a point and a vector, we use this. And this is a vector. Right. Actually, when we get to a higher level, the notation of a point and the notation of the vector will be the same. Because the vector, we can move them freely. Let the tail end be at the origin. In that case, a point is the same as the vector, and the vector is the same as the point. So that's why in higher level math book, they write the notation of a point and vector the same, preferably actually in this form. So they write vector just using the parentheses. Right. And then as you see, the v1, v2, that's regular faced, that vector both face, so we have to distinguish those. And that called the x and y components of a vector v, that is both face, and respectively, right? So, and with that, we say the vectors are equal if u1 equal u2, u1 equal v1 and u2 equal v2, right? So that means we have one vector in position vector, and there's a bunch of vectors as long as same location. Sorry, that was wrong. As long as vector has no location, as long as they have the same length or the magnitude and they point in the same direction, the vectors are the same. Once again, same direction, same magnitude. However, if we write in this component form, then the first component are equal, second components are equal, then the vectors are equal. Right. Now, if we have two random points outside like this, how do we write the vector? Right. So we have the point P and Q. Then the vector PQ is given in that form. And the magnitude and the length is given in this form. By the way, this is some books, some different books, they use different notation, such as they use 2 bars. For the magnitude of the vector as opposed to just a single bar. The reason they just want to distinguish between the vector and the scalar. 2 of them meaning a magnitude, 1 pair meaning absolute values. So they just want to distinguish those two. But then again, when we get to high level, it doesn't matter. Right. I said, so it is, of course, formulas are nice and all, but if we have P and Q, then vector PQ is going to be equal to Q minus P. So see, point Q, x2, y2, P, x1, y1, and we subtract them. And this, of course, is the tail minus the head. I got them backward. So we go from P to Q. So Q is the head. Right. So the head minus the tail point. Right. Head minus tail. Right. Now if we are given in the component vector like this, then well, this is just the Pythagorean theorem. Right. So first of all, we have the triangle here. The distance, the magnitude PQ is equal to square root of that one square plus that one square. And if in the component we have V1 and V2, notice that's just a regular face and not the whole face. The whole face reserved for vectors. Right. So Pythagorean theorem to find the magnitude of a vector. Right. Now given those points, find the components and the magnitudes of the vector. So OP, so the head, the final point, minus the initial point. Point P, -3 and 4. Now this is where we relax the notation. Even where we subtract the point like this, we can also use the bracket if we want to, but I just use the parentheses. And then we just subtract. -3 minus 0, 4 minus 0. Right? So that is vector OP. If we want the magnitude, again, if you want to use 2 bars, perfectly fine. Will be square root of the square of the components. That's going to be 5. So simple enough, right? Final minus initial, head minus tail. Right, vector PQ is going to be Q minus P, final minus initial, head of the vector minus tail of the vector, Q 6 and 5. I write that as a pawn, and then P negative 3 and 4. Six minus negative 3, that's going to be 9. 5 minus 4 is 1. So 9 and 1. So if we want the magnitude, I just use 1 bar and 9 square plus 1 square, square root of 82. Right. So PQ, Q minus P. Right. Just like that. Right. Now, if we don't have the vectors as pawn, we just have components, then we just add or subtract corresponding components. That should be easy enough. Right. So look at the first example. Let vector u be negative 1 and 2, vector v be 2 and 3. What is u plus v? So we will add the vector first. Negative 1 and 2, plus 2 and 3. Add the components. Negative 1 plus 2 is 1. 2 and 3 is 5. So the magnitude of 1 and 5 square root of 26. Right, simple enough, right? So normally we can add, we can multiply by scalar. So we just say 2 times u minus 3 times v. And just like other operation, multiply and multiply. 3 times 2 is 6 and 9, and then we subtract negative 2 minus 6 minus 8, 4 minus 9 minus 5. Right. So if we have a calculator and you just want to use that, because there's no big deal here, I've just used the curly bracket, second parentheses, like negative 1 and 2. So we can use that as a vector if I choose to. Alright, so in that case I will have 2 times negative 1 comma 2, second parentheses to close the bracket, minus 3 2 comma 3, second parentheses, and that's what we have. Right. Unit vectors. So now we define the length of the vector. We use 1 border. A unit vector is any vector of length 1. So unit meaning the length equal to 1. The coordinate of unit vectors I. So we define I in the x component, the length equal to 1, and we define I is 0 and 1. And then j is vector point in the positive y-axis, will be 0 and 1 for j. In that case, we can say 3 and vector 3 and 4 is 3i and 4j. So instead of write the vector u1 and u2, so you can, for example, if you say vector u has the first component in the x-axis, second component in the y. So don't use the subscript x and y, because the subscript x and y reserved for something else later. So we use 1 and 2, first component, second component. If we want to, we can say this as u1 times the vector I is for the first component, and then plus u2, also scalar, the vector j is a vector, right? So the first one times I, the second one times j, and then add them. Because if we think about that, it's very simple, right? So if you write like this, we have u1, I is 1 and 0, plus u2, j is 0 and 1. And when we multiply them out and add, we have u1 and 0, 0 and u2. And when we add, we have u1 and u2. Right, and now we define the unit vector. The unit vector is the vector whose length equal to 1. Now, and with the unit vector, we say the vector that have v divided by magnitudes of v are the unit vector parallel to v. And if we want that vector have some certain length, we just multiply by c. Right, let's look at the example. Consider the point P and Q, 5 PQ and 2 unit vector parallel to PQ. So first, find PQ, easy, right? PQ is Q minus P. Q 1 and negative 2 minus P. I just copied backward, right? Q is 6 and 10. And P is 1 and negative 2. So subtract, we have PQ, 6 minus 1 is 5. And 10 minus 2 is 12. I write in the vector notation, triangular bracket. Right, PQ, Q minus P, 5 and 12. Right, so we have vector PQ is 5 and 12. Right. Next we find the unit vector parallel to PQ. So first we're going to take the vector PQ divided by the magnitude. When we divide by the magnitude, we have the unit vector parallel to V. So in that case, we have 5 and 12. Divided by the magnitude, 5 square and 12 square. So that is 5 and 12 over 5 square, 25, 12, 144, and that should be 169. Square root of that is 13. So 13 or 5 square plus 12 square. All right. And each of them we divide by 5 over 13, 12 over 13. All right. So that's one of them. Remember, when we talk about parallel, it could be pointing in the same direction, or it can might point in the opposite direction, as long as they can align into a straight line. They are parallel. So here's one of them. The other one is opposite to this. We say negative 5 over 13 and negative 12 over 13. Right. Next, find two vectors of the length 2 and parallel to PQ. Right, and that's easy. Now that we have the unit vector multiplied by 2, unit vector has length 1 multiplied by 2, that vector will have length 2. Right, so if we want 2 times that, and then parallel to PQ, we just say 2 times PQ over magnitudes of PQ. And if we want parallel, so parallel can be either direction. So plus or minus 2 times Don't put a dot there. That will be misleading later. 13 and 12 over 13. Multiply the plus or minus 2 inside. We have plus or minus 10 over 13 plus or minus 24 over 13. So those will have length 2 because we multiply 2 to a vector that has length 1. Right. Next. All of a sudden we switch the notation, but like I said, don't worry at all. We can just use 1 bar or 2 bar, doesn't matter. If we want to be clear, we use 2 bars, but like I said, 1 bar works just fine. In physics, they could use 1, they can use 2. The angle could be alpha, could be theta, or any angle. But the thing is, when we have the vector v in that direction, will be decomposed into 2 components. This is a and b, but we can say the vector v will have 2 components of a and b. And only that, we have some basic trigonometry here. Let's say there's an alpha angle there. So we say sine is opposite over hypotenuse. We cannot really use v, so we have to use magnitudes of v. Because if we use the vector, that doesn't make any sense. They have to be scalar, have to be a number, so put absolute values or magnitude in it. So in this case, we will have b equal to v sine alpha, and then cosine of alpha adjacent over hypotenuse. So just have v cosine of alpha. So the vector will be even in this form. So v equal to magnitudes of v cosine magnitudes of v sine. Next we have the properties of the trivial or obvious properties of vectors. I'm just going to put all of that there. Let's go to some application, kind of simple physics application. Right. So assume the water in the river move southwest 45 degrees west of south at 4 miles per hour. If a motorboat is traveling due east 15 miles per hour relative to shore, so the boat just goes straight east. However, because even though it goes straight, but because of the water flow in that direction, so the actual boat that relative to the water is going to be this direction. So in general, the velocity with respect to, or the vector with respect to g, actually they're not called g, that you refer to as a ground, equal to velocity with respect to water plus the velocity of the water. So if we want, what is the question? Determine the speed of the boat and the direction that heading relative to the moving water. So meaning that we want velocity with respect to water. So we just subtract the w on the other side. Right, so that's what we have. Now, let's look at the vectors. What do we have? Assume the water river moving southwest. So first of all, I'm talking about the water here. So the first one I'm talking about is W, the vector W, southwest 45 degrees. So and then it is 4 miles per hour. So we can say this is length is 4. So 4 is not the vector, 4 is the length of the vector. Now if we decompose this into components, so the W, this is the first component and the second component. And the angle is 45 degrees, right? Of course, that could be 45 degrees or 45 degrees here, doesn't matter. All right. So what I learned in physics, and my physics professor say that just look at the triangle with respect to 45 degree. Now we talk about the vector W. By the way, somebody used an underline for vector also. In terms of notation, somebody actually used the underline. So I'm avoid trying to underline anything at random. So first of all, let's say the vector W. We have W1 is adjacent to 45 degrees, so that will be cosine. Is W magnitude times cosine of 45 degrees. Now, this is where the physics come into place. So the thing that will make sense. This point to the left, right? This point to the left. So we will put the minus there. If we want to deal with that, remember the actual angle. Or if we don't want to deal with positive or negative, just think about that is 225 degrees, that big angle. And this will work just fine. But we put the negative here because that makes sense. That point to the left is negative. Right. Magnitude of W is 4, so we have negative 4. Cosine of 45 degrees, square of 2 over 2. So we have negative 2 square root of 2. So that is W1. W2 pointed down, so that will be negative absolute values of or magnitudes of W sine of 45 degrees. So opposite and then adjacent. So simple enough. So negative 4 square of 2 over 2 for sine 45 degrees cancel with 2 square root of 2. So in this case we have vector W equal to W1, W2, and we have negative 2 square root of 2 and negative 2 square root of 2. Both of them are negative. Now, so we have one of them, W. Now the VG velocity with respect to ground or velocity with respect to shore. So with respect to shore goes is. So just that direction. So that's easy. If we want to draw that. Just go in this direction. So in this case we say if we want to, we change VG of sub 1, the first component is 0. I'm sorry. Just say this. The first component point to the right, exactly that. 15 miles per hour. So this is going to be 15. And VG second component does not go up or down, so it's going to be 0. So the vector velocity with respect to ground is 15 and 0. And then finally we just do this. Velocity with respect to the water equal to velocity with respect to shore minus the velocity of the water. So 15 and 0 minus 2 square root of 2 minus 2 square root of 2, and do that we have 15 minus, so I just get an approximation. 15 minus a negative plus square root of 2 square root of 2. So about 17.8. And then 0 minus negative 2 square root of 2, so that 2 square root of 2 like 2.8. So this is the velocity with respect to water. So we're going to be kind of in that direction. Now if we want really want the direction, we can always do this. Tangent of an angle is equal to y over x. So alpha is tangent inverse of y over x. Make sure that we need to check the quadrant. If it's not right, always add a pi to it. So we have this in the, when we go to polar coordinate. So check the quadrant. So in this case, we just take the tangent inverse. If I use tangent inverse, I will use in degree mode. Yep. Tangent inverse of y over x, 2.82 divided by 17.8, about 9, so about 9 degrees. So technically we can say the direction it moves like this, which is in the north 81 degree on the east side. So north 81 degrees east side. So all thereabout. Right, next, this will be easier. A child pulled a wagon with a force 20 pounds. So we know that in this case, the force that he pulled, that is 20 pounds. So if we decompose it, we have 20 pounds at the 30 degrees angle. And I'm going to put 20 here. Doesn't mean the vector is 20, I mean the length, that is 20. So in that case, we'll decompose that into two components. So we just said vertical component and horizontal component. Right. So the horizontal component is adjacent to the angle. Adjacent is cosine. So is the magnitude of the force times cosine, because that is adjacent. So 20 cosine of 30. Cosine of 30 is square root of 3 over 2. So that gives us, I just get approximation. Never mind. The exact values. So we have 3 over 2. So we have square root of 10 square root of 3. That is F1. And because it's point to the right, it's positive. Right. F2. Second component. Like I said, sometimes use 1 bar or 2 bar, doesn't really matter here. F2 is opposite to the angle. Sine of 30. 20 sine is 1/2, so it's going to be 10. So F2 is going to be 10. Or we say the vector F, again both face. First component 10 square root of 3, and then 10. Right. So the force F is given in the vector form, like that. Right. Next we have this example. 400 pounds engine. So this one had 300 pounds that points straight down. So because it points straight down, we can say the x component, it doesn't go anywhere left or right, but it's going down. So all the force point down at 400 pounds for the second component. So that's easy to know, F3. Right? Because the weight always point straight down, 0 and negative. Next. Because this is 60 degree and this 60 degree, the force, the magnitudes of F1 and F2 are equal. So we have F2, the magnitude equal to the magnitudes of F1. And for simplicity, let that equal to just the regular phase F. Right. So in that case, let's decompose these two forces, F1 and F2. Right, so we have 60 degrees. I actually have the projector here, so it's right. So to use the projector, place that point right where the line is, and 160 degrees, so which is right here. Connect that back to the point. So the F1 point in that direction in the vector form, and then F2 also 60 degree but on the other direction. The magnitude is about the same, so then we can decompose this. When we decompose this, we will have two components. Now it's difficult to use because we already have the subscript 1 for vector 1 and not the component. So calculus 3, actually the notation is extremely important. Right, first decompose the F1 into two components. This component I just said, because that is adjacent to 60 degree, it's going to be F times cosine of 60 degree, where F is the magnitude of F2 or F1. So that is F1 cosine of 60 degrees. Now this is opposite. Opposite is going to be sine. Right, so that's the first one. Now the vectors. This is going to be the same. The notation is going to be f cosine of 60 degrees, because one again it is adjacent to 60 degrees. However, we're going to throw in the negative because it's pointing to the left. So that the physics come into play. Always draw a right triangle with acute angle and then determine positive or negative by the fact up and right is positive, down and left negative. Now, so we have one component and the other component is going to be f opposite to 60 and still positive. So even though we can decompose like this, we can put both of them into this. Bottom line is we have the first vector is equal to f cosine of 60, f sine of 60 degrees, f2 negative f cosine of 60 degrees, and then f sine of 60 degrees. And then f3, we already say that's 0, negative 400. Now also one thing in physics, if the system is not moving, meaning all the vectors add up to 0. So because it is suspended, so nothing moving. So f1, the sum of 3 vectors equal to a 0 vector. So notice that this is a vector 0. Like that. So that is the notation for the vector 0 or 0 vector. Right, so when we add all this up, add all the first component, we have 0. On the left hand side we have 0. On the right hand side we have 2f sine 60 degrees minus 400 equal to 0, 0. Yeah, so I just add side by side here. The right hand side is supposed to be 0. So from here we say 2f sine 60 degrees minus 400 equal to 0. So we can find the magnitude of the force is equal to 400 divided by 2 sine of 60 degrees. Right, are we still in degree mode? Yes. So we have alpha y equal to, hit enter, give a fraction, so 400 divided by 2 times sine of 60 degrees. We have about 230 pounds. So the force, the magnitude of the force for each one text is 230 pounds. Right. So, of course, if we put both of the chain straight up, then each of them will take 200 pounds. But because they just suspend at an angle like that, so that means they contribute some of the horizontal component, and horizontal component cancel out. So there's some waste in the horizontal component. Right. if we have put both chains hand up straight up perfectly like this, and each one of them will take the weight of 200, but because they're with an angle, so we have to have some more to compensate for the horizontal component of the force. Right. So that's fairly basic. We haven't done any calculus yet. It's just a review in with calculus, but it's good. Just basic of the vectors in the plane into the measurable space. Anyway, I stop this video, the first section here. Thank you for watching.